Hello student, I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss three-dimensional representation of organic molecule. Last class I have discussed a structural representation of organic composition, organic compounds, not composition. Last class I discussed a structural representation of organic compounds and some this problem I have discussed. Now I am going to discuss three-dimensional representation of organic molecule. The three-dimensional, that is 3D, structure of organic molecule can be represented on paper by using certain convention. For example, by using solid, how you will represent solid? Then it is represented by a dark line, black dark, and this using a solid, that is a dark black triangular line, and dashed means from 1 point, then 2 point, then 3 point, 4 point, continuously increase. Okay, starting from 1 point, next second 2 point, again 3 point, 4 point, like that way you can increase around just length around 1 inch. Then that is called dashed wedge formula. Dashed WEDGE wedge formula. The 3D image of a molecules form a two-dimensional picture can be perceived. Okay, for this I told you, for solid, that is the dark line, just little rectangle, triangle, just like a triangle, little dark, that is for solid. And dashed wedge formula, the 3D image of a molecule from a two-dimensional picture can be perceived. In this formula, the solid base is used to indicate a bond projecting out of the plane of paper. Plane of paper, only two-dimensional picture you can show, only two-dimensional length and breadth, but height, and if you want to show height or if you want to show depth, then how we will show like this? Then that time solid wedge bound towards observer, that means from the dark bond, that is called solid wedge bound towards observer, means front side, it will tell about the front side. And dashed wedge, DASH, it is dashed wedge, just like I told you, point, then little double point, triple point, 4, 5 point, like that. Then that type of symbol, that is called dashed wedge, or little broken also you can tell. Then that bound shows away from observer, one black solid wedge that will tells bound towards observer, and this dashed wedge that will tell bound away from observer. The dashed wedge is used to depict the bond projecting out of the plane out of the plane of paper and away from the observer. Waves are shown in such a way that end of the beige is towards observer. Means one point what you have written, that is attached to the carbon, and that is again little thickness, that things that will be to away from observer. Okay, broad, that is a broad end, you can tell, point and broad end. Broad end of the wedge is towards the observer. The bonds lying in the plane of the paper are depicted by using a normal bond. Means length, breadth, that size, that you can show by normal bond. 3D representation of methane molecules on paper. This it will be like this only. Two bond will be normal because it is on paper, plane, same length, like in the length and these things. Lengthwise, breadthwise, you can tell in two dimension means length and breadth. No, you can say this height or depth. Then that is a common. Two bond will be common. If you want to see 3D structure of a molecule, then two bond will be normal and other two bond will be just like out of a plane. One towards observer and other away from observer, but it will be out of plane. Okay, then bonds in the plane of paper, that is the two. Simply you consider that in a CH4, anything it is lying on the earth, length, breadth and up. If something is coming up, then that is if it is towards observer, then black line again little so, but out of plane only. They are above the plane. These two are above the plane. One towards you means observer, other away from observer, and other two bond, that is a plane. Okay, just it is just like this is called. If you will thickness, you will consider, then that will be 3D, three-dimensional, length, breadth, that is on the plane, and other two bond will be above the plane. One towards observer and other away from observer, but above the plane. I will try to send this structure. Okay. Now again further I am telling you molecular model. Molecular model in your college or school you might have seen. Molecular models are physical devices that are used for a better visualization and perception of a three-dimensional shape of organic molecule. That it will be generally in college school it will be there. It may sometimes it may be of plastic or wood. You can show very clearly all four bonds. Just to imagine that anything's cube, as for example cube. Ludo you are playing, that one, this will be there. That will be 6 point will be there. One side, one other side, 2, 3, 4, 5, 6. Means a square, any square you can take made up of wood. Then that is the best example of three-dimensional structure. Anything wood also, suppose any ordinary wood you will take, then it will have length, breadth, height. Anything which has a length, breadth, height. Cube I told you that structure is very good to understand. Cube made up of wood or any material, maybe of plastic also, or maybe of stone also. Then they should have some length, breadth, height. That is called three-dimensional, 3D. Then molecular models are physical devices that are used for a better visualization and perception of three-dimensional shapes of organic molecules. These are made up of wood, plastic, or metal and are commercially available. Commonly, three types of molecular models are used. Three types of molecular model. First, framework model. Second, ball and stick model. And third, space filling model. Three type of model is possible. First, I told you frame model. Just in a frame it will be there, you can just adjust it. Framework model, that model may be of any molecules, ethane, methane, just only you have to join to each other, every parts, just like you have to assemble, then it will give some shape. Their scope will be there to adjust. Then three types means first type I told you, that is the framework model. Second is the ball and stick. Then ball will tell about the atom and stick will tell about the bond. In the middle, just as for example, carbon is there, carbon CH4, 4 hydrogen you have to adjust. Then carbon will be in the middle. Then in that way, one material will be in the middle. From there you can adjust this stick, 4 stick you can stick. Then that this stick there you will adjust. And that will tell about the bond. And the end for each bond you can adjust one ball. Then that ball may be of different color. Different color maybe same color also, different color also. Suppose you want to show hydrogen only, 4 hydrogen. Then all 4 will be of the same color. That is telling about the hydrogen atom. With bond you can see. Carbon will be black. In that stick you have adjusted, and after that and the bond end one ball you will adjust. That ball is telling about the atom. If all atoms are same, as for example hydrogen, then 4 stick with 4 head. Head means air. It is telling about the atom. Then same atom means same color. If suppose different 3 types of atoms are there, then one may be, all 3 will be different color. One may be red, other will be green, third will be blue, correct? Then 3 different color. And if all are 4 different atoms, then head will be 4. Means ball what you adjusted, that will be 4 different color. Okay, then like that way you can understand. Then first I told you that is the framework model. Second also I told you ball and stick model. And third, a space filling model, means a space you can adjust in a space. You can see everywhere which direction, suppose 4 bonds are there, then in which direction all are there. You can understand in a space. And sometimes you will find only in one plane. Thickness will be not there, only in plane will be like that. Only in one plane one will be there center, and other will be near the center, only in the plane it will be there. Then this I have told about the, you can say this molecular models. Okay. Then this only the bonds connecting the atoms of a molecule and not the atoms themselves are these things. Diagram also I will try to send it. This model emphasizes the patterns of bonds. This model, whatever I discussed, three model, then this model emphasizes the pattern of bonds, in which direction which bond is there. It is not necessary that now 4 bonds are there in 4 direction. Then in 3-dimensional, in a space, by that type of model you can understand very quickly what are the angles between the 2 bonds. What are the angles between the 2 bonds? You can understand very easily. Okay, on paper you can't see, but in a space, by model you can understand that all four bonds are in which direction and what are the angles between the 2 bonds. This is the benefit of molecular models. Then this model emphasizes the pattern of bonds of a molecule while ignoring the size of atoms. Atom may be different size. In the this is actually in framework model what I told you. Here you will ignore the size of atoms. In the ball and a stick model, both the atoms and the bonds are shown. Bonds also I told you that a stick will tell about the bond and head will tell about the ball will tell about the atoms. Balls represent atoms and the stick denotes the bond. Compounds containing carbon double bond. Suppose you have to show the double bond, carbon double bond in case of ethene, then that can be represented by using springs in place of sticks. There double bond if you want to show, then for that a spring will be there. That spring that will tell about the double bond. A spring. Then a spring, you know that length can increase or decrease. Then because their electrons will be in movement, then there will be some, you can say, bond length little minor may change. Okay, and molecules will be in motion also, little it will move. Then that's why a spring will tell about the double bond. Okay, then it is actually represented by using a spring in place of a stick and double bond. These models are referred to as a ball and a spring model. That time it is called ball and a spring model if double bond is there. The third, the space filling model emphasizes the relative size. It will tell about the size. First was not telling about the size. Third is telling about the size. Means a space filling model emphasizes the relative size of each atom. Atom is small or big, that will tell. All atoms are not the same size. Hydrogen is different size, chlorine is different, fluorine is different, oxygen is of different size, correct? Nitrogen is of different size. All atoms of different atoms, means different elements are of different size. Don't think that all atoms are same. Hydrogen atom is different, maybe very small. Helium may be little more, lithium may be little more. Like that way, beryllium may be little more, boron further more, carbon further more, nitrogen further more, oxygen further more, different size. Then in third I told you that in third representation, that is the space filling model, emphasizes the relative size of each atom based on the van der Waals radius. Bonds are not in this, bonds may not be shown. Only molecules will be, different atoms will be shown. Bonds are not shown in this model. Only different size of atom will be shown. It conveys the volume occupied by each atom in the molecule. That will tell about the how big is the molecules. In addition to these models, again one more this is there, model can tell, but that is not the model, that is the computerized graphic. Computer graphic, it will be computerized. Computer graphic. From that also we can understand the, in computer, by the use of computer, that model, that atoms also we can see. Bond also we can see. Atom also we can see. Angle also we can see with the help of computer. That is called computer graphic. Computer graphic can also be used for molecular modeling. Then this I have discussed about the molecular models. This is actually in advanced study. When you will go for BSc or MSc, then you will see all the things. You need also to see all the things. Now simply suppose H2O. H2O, you are just in paper, you are writing H2O. But what is as a structure H2O? 2 H and O, how all are related, very clear cut picture you can see in 3-dimensional. Length also you can see, both hydrogen bond you can see, oxygen you can see, what they are doing. They will come sometime, if double bond is there, they will come little close and then will go far. Like that way, spring like that, it will, obviously you will see that in real practice it happens with a double bond. Then this I have discussed. Now I am going to discuss classification of organic compounds. These are very, very important in the initial stage. Those who are not knowing organic compounds, for them these are very, very important, basic. Then now I am going to discuss classification of organic compounds. The existing large number of organic compounds and their ever-increasing number has made it necessary to classify them on the basis of their structure. Organic compounds are broadly classified as I am telling now. First, actually large number of organic compounds are there. Then how will you separate it? How will you classify? Then on the basis of their structure it is classified. Then here in a broad way it is classified into 2 ways. First, acyclic, acyclic, acyclic or open chain compound. Open chain compound, just like a chain structure, last class I have discussed. And second, cyclic or closed chain or ring compounds. That also last class I discussed, that all atoms are joined to each other. Then that is called closed or ring or cyclic. 3 names are there: cyclic or ring or closed, because all are joining each other. That's why it is called cyclic or closed or ring. Then many organic compounds will be in this form: ring or cyclic or closed chain. And first I told you that was acyclic, a straight way, no turning, no joining to each other. Means all are not joining, just a straight way. End and both ends are not joined. Both ends are not joined. It is open, just like our hand, both hand. Then that is your first type, and second type is cyclic, means end is joined. First end and last end both are joined. Maybe 4 or 5 atoms and all are joining to each other, first and last also. Okay, then that is the cyclic or closed or ring. Then this I have told you base main 2. In ring also, in ring or cyclic or closed, again it is a two types. First type is homocyclic, or second type is heterocyclic. Hetero means different. Homocyclic is also known as carbocyclic. Carbo means carbon. Carbo means carbon, cycle of carbon. Generally organic compounds, carbons are there. That is compulsory, essential. Then some generally all carbon will be in any compound, organic compound, carbon is must. Sometimes only carbon will be there. Sometimes other than carbon also may be there. Maybe oxygen, maybe nitrogen, maybe chlorine, bromine, iodine may be also attached there. That's why that is called heterocyclic. Other than carbon, I mean carbon may be, and with carbon other may also be there, and that is called pure carbon. One will be compound will be pure carbon, that is hydrocarbon, also called carbocyclic. And other is other, when other atoms are also present with carbon, then it is called heterocyclic compound. Now homocyclic, under homocyclic is again divided into two groups. Homocyclic is also divided into two groups. One will be alicyclic compound, ALI, alicyclic. Okay, what first I told acyclic, ACYCLIC, acyclic or open chain, that is the acyclic. Here alicyclic, ALI, alicyclic compound, and other is aromatic compound. Okay, means homocyclics are further divided into two groups, alicyclic and aromatic compound. Then now aromatic compounds means that will be two types again. Aromatic compound will be of again two type. One type is called benzoanide compound, means benzene will be there. Benzene structure will be there. Six atoms are joining to each other, and each carbon is joined by a hydrogen, one hydrogen, alternate double and single bond. Alternate double and single bond. Last class I have sent so many diagram. Then that is called benzene structure. 6 carbon atoms all are joining to each other by alternate double and single bond. And sometimes benzene structure will be like that, 6 carbon will be there, all are joining, and in the middle one circle will be there. What does this circle means? Because alternate double and single bonds are there. Then these bonds are moving. Means where double bond was there, after some time it will be single bond, and where single bond was there, that will become double bond. Then this will be rotating always. That's why cycle inside the benzene ring, one cycle is written, one circle is written. Okay, you might have already seen one cycle will be there, that represents that double bond is becoming single bond is becoming double bond, and this is happening because always electrons are moving. Then that structure is called benzene structure. Then that's why one in aromatic compound, one will be benzoanide compounds. Benzoanide, and this another will be non-benzoynide compound. Non-benzoynide means compounds will be there, and that will be benzene will be not there. 6 carbon may not be there. Non-benzoynide, maybe 7, maybe 8, correct, like that way. If only 6 are there, that is called benzonoid, and that both are aromatic. Both are aromatic. Some conditions are there. Then benzene is aromatic compound, but other compound is also there. They are in ring form, but more than 6. More than 6, you can say atom may be there. More than 6 atom. That is also, they are aromatic. Then that is called non-benzoynide compound. Now I am going little details of acyclic or open chain compound. First, what I told you, acyclic, ACYCLIC, acyclic or open chain compounds. I will go. I will give some example for all the things. I will give some example. What I discussed now, classification, I will give some examples for all. Then first I am giving example of acyclic or open chain compounds. These compounds are also called aliphatic, popularly known as aliphatic compounds, and consist of a straight or branched chain, maybe sometime generally a straight, sometime branched also, but open. It will be not closed, it will be not in the ring form. Ends will be not joined. Then that is called aliphatic and consist of a straight or branched chain compounds. Example I am telling you, that is the ethane, CH3, carbon, 2 carbons are joined by each other, carbon by single bond, and each hydrogen is joined by 3 hydrogen, 3 each, total 6, C2H6. This is a first example of alicyclic or open chain compounds. Now isobutane, that is in the branch form. Second example, that is the branch chain compound is isobutane. Iso means, you know that iso means equal, same. Iso means same. Then is a isobutane. Butane means there will be 4 carbon. Butane means 4 carbon, and ane is there, N, that is the alkane. Then alkane meaning already I have told you, single bond. It means carbon will be in the middle, and with the carbon left and right CH3 will be there, and third CH3 will be up, means 3 CH3 will be there, and fourth valency will be hydrogen. Carbon has 4 valency, then one middle carbon is joined with 2 CH3 left and right, and 1 CH3 upside, then 3 valency is over. Fourth valency is covered by hydrogen. Then now this is total become 4 valency. Then this is called isobutane, means it is a branched. Every side same group is there. That's why called isobutane. Okay, isobutane, 4 carbons total. 4 carbons are there. 3 straight and 1 above, including central carbon, one left side, other right side, and again upside, 4 carbon. That's why butane, and 1 hydrogen will be there. It's called isobutane. This is a branched. Now other example I am telling you, acetaldehyde group, I told you CHO group. CHO HO group is called acetaldehyde group. Then now CHO group is called acetaldehyde. Then now you can see in acetaldehyde carbon CHO, then CNH single bond and CNO double bond. Okay, oxygen has two electron, they will make a bond, and this thing is a double bond. Then oxygen this 2 electron oxygen and 2 electron carbon, means 2 valency of carbon and 2 valency of oxygen. Total 4 electron, each electron, for each electron 2 electrons required. 1 each. Then here 2 each means double bond. Double bond will be there. Then now you see that carbon 2 electron is used up in making the bond with oxygen, double bond, and 1 electron is used up to make bond with hydrogen. 3 is used up, and 4th one, that is used with methyl group. They have made bond with CH3 group. CH3, 1 electron in 1 valence electron will be there, and 1 carbon will have electron. Then that C and CH3 one group. Then total 4 valency of carbon I told you. Okay, used up. 1 double bond and left and right single. Then this is called acetaldehyde. CH3 CHO, CH3 CHO. Then CHO group is aldehyde group. This is called aldehyde group. If CH3 is attached, then it is called acetaldehyde. And if in the place of CH3 H will come, H hydrogen, then that is called formaldehyde, formica. It came from the word formica. Ant, from the ant it is found. Then if H is attached with aldehyde, then it is called formaldehyde. If CH3 is attached, then it is called acetaldehyde. Then now you can see this is also branched compound. Now another example I am telling you. Another example of chain compound, open chain compound, that is the acetic acid. Acetic acid I told you its group is COOH group. COOH group, that is carboxylic group. In all acid this group will be attached, COOH. Then here COOH, then here what will happen? Here C and O, 1 double bond will be there. Just like aldehyde, COO double bond was there. Here also one double bond will be there. And other oxygen, this will join, it will be in the middle. One electron will make bond with hydrogen. Oxygen 2 electron is there uttermost, then 1 electron will make bond with hydrogen, OH, and now another electron will make bond with C means COH, and other bond COO, then it is called COOH. COO, upside you can write COO, and left side C, and again one bond is attached with oxygen, and another bond is attached with hydrogen, O and H one bond, and O and C another bond. Then now carbon balance you can count how many valence used up. Then only 3 valence is used up, COO and CO. What about the 4th one? 4th one had not used. Then this fourth electron is now joining with CH3 group, methyl group. They have made bond with methyl group, CH3. Then now it is called CH3 COOH. CH3 COOH. Okay, then this is called acetic acid. Acetic acid. Acetic acid. CH3 COOH. COOH common. In all acids, this group will be there, COOH. But if CH3 group is attached, if a CH3 group is attached, that is called acetic acid. And if in the place H will come, then it will called formic acid, just like formaldehyde. I told you, formaldehyde, acetaldehyde, CHO group was there. If CH3 is there, then acetaldehyde. And if H is there, then formaldehyde. And like that way, group acid group is there, carboxyl group. If CH3 is attached, then acetic acid. And if H is attached, then formic acid. And both origin is from formica, which is found in ant, ant. Then this is the example of open chain compound. Open chain because they are all are not joining. First and last are not joining. All are open. Then this I told a straight and open chain organic compound, organic molecule. Now second I am giving you examples of, I told I will give examples of all. Alicyclic. Alicyclic or closed or ring compound. Three names are there. Alicyclic, closed, chain or ring compounds. Here alicyclic, aliphatic cyclic. Alicyclic is also called aliphatic cyclic compounds. Then alicyclic compounds contain carbon atoms joined in the form of a ring. Ring may be of triangular, maybe 4-membered, 5-membered, 6-membered, 7-membered, 8-membered ring. It is not like that, only 3, maybe 4, maybe 5, maybe 6, 7, 8, like that way. Then this will be in the form of ring. Alicyclic compounds contain carbon atoms joined in the form of a ring. That is the homocyclic, all are carbon only. All are carbon only, that is the homo. Homo means same, homocyclic. Sometimes atoms other than carbon are also present in the ring. That is called heterocyclic. Hetero means different. Then now I am telling examples. Okay. Then here you can see cyclopropane. Cyclopropane. Propane means 3. Propane means 3 carbon you are talking about. 3 carbon. Then these 3 carbon are in the form of, all 3 carbons are joining to each other. Then it is just like a triangle. Triangle. Last class also I told you. Then just 3 points. 2 point base, 1 point up. It will form triangle. Then 3 carbons are there and all 3 carbons are joining to each other. Then this is called homocyclic. Like that way, other example of homocyclic. Then now it is a 6 atoms of carbons are attached. Just example is a benzene. Then but here one hydrogen was there. Each carbon hydrogen, one hydrogen was there in benzene, because alternate double and single bond was there. Then their covalency is completed, because one carbon was making double bond. Then one side double bond, other side single bond. Then 3 valency is over, 2 plus 1, 3. And fourth one was with hydrogen. Then C6H6, that is the benzene. That is also examples of cyclic, homocyclic, cyclic you can tell. Okay. Now this cyclohexane. Now here 6 6 carbons are attached and each carbon to 2 hydrogen is there. In benzene only one hydrogen was there, C6H6, but here C6H12. Because everywhere single bond is there. Then 2 valency of carbon is used in making bond with with neighboring carbon. Then 2 valence was remaining. That will make with valence electron, 2 valence electron, they will make bond with 2 hydrogen. Hence each carbon will have 2 electron, C6H12. Then it is in a ring form. That's why it is called cyclohexane. All alkane, ANE means alkane, alkane means single bond. Now another example I am telling you, ring, that is the cyclohexene. Cyclohexene, ENE, means 6 carbons are there, but between the two carbon, double bond is there, one double bond is there. In this ring, one double bond is there, means between the 2 carbon, double bond is there. Then double bond means ENE, double bond. And 6 carbon was there, hence the name has been given hexene. Hex means 6, and anywhere either two double bond or triple bond, but double bond, any double bond is there, then a name will come in the end, ENE. Then it is a cyclic, that's why its name is cyclohexene. Now like that way I am telling about the example of heterocyclic. Then here 5-member ring I am talking about. 4 carbons are there. 4 carbons are there and one other atom is there, oxygen. Then total 5, including oxygen, it is 5. Then all 4 carbons are joined, okay, through oxygen. Means 2 carbons, last 2 carbons joined with oxygen. Then it is a 5-membered ring, and it is the example of heterocyclic. This is example of heterocyclic, because it is also cyclic form. All are joined, including oxygen. Oxygen is joining with 2 carbon, left side, right side, and all carbons are joining to each other. Then total 5-membered ring, including oxygen. The oxygen is different from carbon. That's why it is called heterocyclic. These exhibit some properties similar to those aliphatic compound. Okay, these compounds will show some properties similar to aliphatic compound. Now I am coming to the aromatic compound. Aromatic compounds are a special type of compounds. Okay, actually this is here if you want study details, then higher classes you will study details. Here just like introduction. Then aromatic compounds, these include benzene. Benzene is the best example of aromatic compound. Benzene and other related ring compounds. 6 carbons should be there. Then other related ring compounds, that is called benzenoid. Benzene is only 6 carbon, but if any compound is similar to benzene, then that is called benzenoid. Okay, other related ring, in that if benzene ring is there, other compound is there, then that is called benzenoid. Like alicyclic compounds, aromatic compounds may also have heteroatoms in the ring. Means total 6 will be there, but 1 will be other than carbon. Then that is also called heterocyclic aromatic compound. That is also aromatic. Aromatic means aroma, a special type of a smell will be there. Okay, when it will burn, it will give a special type of a smell, aroma. Then here, in 6-member ring, sometimes other than carbon will be also there. Then that will be called heterocyclic aromatic compounds. I am telling you some examples. Some of the examples of various type of aromatic compounds are now I am giving example. As for example, benzenoid aromatic compounds. Benzenoid aromatic compound. Benzene already told you that 6-member carbons are there and alternate double and single bond is there, and each carbon only one hydrogen is there. That is the benzene. Last class I have sent. Now aniline. If in benzene ring one hydrogen will go and in its place NH3 will come, NH3, then that is called aniline. That is also example of benzenoid aromatic compound. C6H6 was there. Now one hydrogen replaced with one NH3. Then now C6H5 and NH3. C6H5 NH3. In the ring NH3 is attached. Then this is called aniline. Don't forget. Very common example. If two rings are joined to each other, then it is called naphthalene. Now here what will happen? That each ring two hydrogen will go. Each ring two hydrogen will go, and they will make a bond. They will make a bond. Continuous ring it will make. Continuous two ring it will make. Then naphthalene is the best example, that now two benzene ring is attached, but where they are attaching, common place will be single bond. Okay, means here you will characteristic is that in naphthalene, anthracene three ring will be attached. In anthracene 3 ring will be attached. Okay, and what is the characteristics? In benzene you have seen alternate double and single bond was there, but here if you will see, if you will start from any one carbon, then you will find that double, single means you have to go continuously in other ring, you have to enter. Other ring means first ring double bond, after that first ring single bond. Now in continuous second ring double bond, again it will come single bond, again double bond, again single bond, again double bond. Now you are entering to the first ring, then that will be single, again double, again single, again double. Means if you will count double and single continuously in a proper way, that is a double. You have started, suppose from the upside you have started double, single. Now you enter to the another ring, second ring you enter, double, single, again double, single, again come down, single, then double, again single, the double, again you are entering to the second ring, single, double, then it will continue double, single, like that. This is the naphthalene. And in anthracene, again same thing will happen. Three benzene ring will be attached. Then again same way, double, single, first ring, again double, single, second ring, again continuous, third, double, single, again you come down, then double means single, double, again second, then third, like that it will continue. That is, then if 3 rings are there, then it is called anthracene. If 2 are there, then naphthalene. Naphthalene is sublime. Naphthalene is sublime. Directly it will convert to the vapor without melting. Then this I have told you about the benzenoid aromatic compound. Now non-benzenoid compound I am telling you. Non-benzenoid compound. It is not benzene. It is just looks like benzene, but it is a non-benzenoid compound, that you will count the total carbon to, then you will get more than 6, 2, 4, 6, 7. You can take example of 7 carbon, not the 6. 6 will be aromatic or benzene, like that. 6 generally will be aromatic only, 6. But here if 7 carbons are there, hepta, and with 7 oxygen is, if it is joined, double bond. Okay, 7 carbon, a ring of 7 carbon, then any one carbon will be joined with oxygen, double bond, then that its name is tropolone. O-N-E means it is telling about ketone, Ketone, O-N means in shortcut ketone. O means ketone, double bond. Then this 7 carbons are there. Then 7 carbon, with 7 carbon rings, 1 oxygen is joined with double bond. Then this is called tropolone. This is the example of non-benzenoid compound. Okay. Now other example I am telling you, but that is the heterocyclic aromatic compound. Heterocyclic, it is a cyclic and aromatic. Then here you will find that it is not necessary that if aromatic is there, then 6, only 6 will be there, 6 carbon will be there, that is okay. One point is okay, but not always necessary that only 6 atom ring will be aromatic, not necessary, that will be, but 5-membered ring also may be aromatic. 5-membered ring will be also aromatic. As for example, furan, F-U-R-A-N, furan. Here 4 carbons are there. 4 carbon atoms of carbon are there, and 5th one is oxygen. Fifth one is oxygen. Total 5 atom. 4 carbon atom, 1 oxygen atom. Then in this 2 double bond will be there. With carbon, left and right, double bond will be there. Up will be single bond, and with oxygen, single bond. 2 bonds are there. Then left, right, carbon, double bond. Third bond upside, that is a single bond, and with oxygen again single bond. Oxygen is making bond with 2 carbon, down 2 carbon. This is the furan. This is the oxygen, because out of 5 1 is oxygen, that is the hetero. This is called heterocyclic, and all are joining to each other, that's why cyclic. And these molecules have aromatic character, that's why it is called heterocyclic aromatic compound. Second example is thiophene. Same way what I told you, in the place of oxygen, if sulfur is there, then it is called thiophene. Thio means sulfur. Like that way, if in a benzene ring, suppose in the place of 1 carbon, nitrogen will come, means 5 carbon and 1 nitrogen, total 6. Then one is the other than carbon, nitrogen, and same way it will be alternate double and single bond, but nitrogen will be there having 1 lone pair of electron, actually, and that is used in the making double bond. Then this here also alternate double and single bond will be there. Only difference is that in the place of 1 carbon, nitrogen will be there, means 5 carbon, 1 nitrogen, total 6. Then this is called pyridine. This is called pyridine. Then this organic, these what I given 3 examples. Organic compounds can also be classified on the basis of functional group. Organic compounds, what I discussed, that is the one type of classification, that is the on the basis of a ring and a straight line or branched. But other classification is there on the basis of functional group, okay, into families. Families are called homologous series. Homo, H-O-M-O, homo, logous, L-O-G-O-U-S, homologous series. Families is known as homologous series because of similarity. Minor difference will be there. There will be similarity, that is called homologous series. Okay. Then on the basis of functional groups into families, you can divide on the basis of functional group in different families, that is called homologous series. Functional group, what is a functional group? Already I have told you, like alcoholic group, OH group, that is a functional group. Carboxylic group, COOH group, one dash will be there, one valence is remaining in all group. OH, one is remaining, one electron is free, just to make bond with other. Then OH group, COOH group, means carboxylic group, aldehyde group, CHO, again one valence is there, free, just they are ready to make bonds with other. Then carbonyl group, amine group, NH2 group I am talking about, NH2 group, NH group. Then these are the different type of functional group. And also these things, ester group, RCOOR, that is the ester. R means alkyl. R means alkyl group, maybe CH3, maybe C2H5, methyl group, ethyl group, propyl group. Okay. Then RCOOR. Then this is if R is not there, only COOR is there, then that will be called ester group, ester. Okay. Actually in flowers, good smell is due to the different type of ester. COOR group will be there, RCOOR. R may be the same, R may be the different, means RCOOR dash. Then R and R dash may be different. Suppose R is ethyl, then R dash may be methyl. Then ethyl methyl ester is called ethyl methyl ester, RCOOR. Sometimes R may be propyl, butyl. Then in flowers plant, different type of flower you have seen. Then a smell will come due to this ester. Different type of esters are found in flower plants and in flowers. That's why a smell will be different. This I told you, advanced knowledge you will get it in higher class, but here only I told you. Then now the functional group may be defined as an atom or group of atoms joined in a specific manner, which is responsible for the characteristics, chemical properties of the organic compound. The examples are, already told you, hydroxyl, OH group. If OH group is attached with any organic compound, then they will have phenolic group, also called phenolic group, OH group is present in anywhere in any compound, that is the alcohol group. OH group is called alcoholic group, alcohol. If suppose any aliphatic compound is there and OH is present, OH group is present. Suppose methyl group is there, CH3, and OH is attached, then there will be the methyl alcohol. This is a poisonous. And if in the OH is attached to this ethyl group C2H5, C2H5OH, this is the ethyl alcohol. Ethyl alcohol is non-poisonous. In all type of wines, this ethyl alcohol may be present. And if with the ethyl alcohol, if methyl alcohol is present mixed, then it will be that it will be poisonous. One should not drink it. Methyl alcohol is deadly poisonous, and if methyl alcohol is mixed with ethyl alcohol, for industrial use, actually it is done, industrial use. In industries, as a solvent, ethyl alcohol is used because people should not drink this ethyl alcohol. This is for industrial use. Knowingly, methyl alcohol is mixed so that people should not drink. But despite that, illiterate people will drink and will die. Many examples are there all over the India, particularly in India. Then ethyl alcohol, OH group is attached, then it is called ethyl alcohol. If in methyl group OH is attached, then methyl alcohol. Like that way, propyl alcohol, butyl alcohol will be there. Then this is the one family. Alcohol is one family. That is the homologous series. Like that way, if aldehyde group is attached with any methyl group, this is attached aldehyde, then it will be acetaldehyde. Methyl, what you are telling, methyl aldehyde, that is called acetaldehyde. Formaldehyde, propanaldehyde, butynaldehyde, aldehyde is attached. Then again they will make aldehyde. All aldehyde will be one family, just like a caste. There is a different caste, means different family, alcohol family, aldehyde family. Like that way, different type of ester will be there. Methyl ester, ethyl ester, methyl ethyl ester, butyl ester. Then all esters are one family. That is called homologous series. Like that way, acid, carboxylic group is there. Then if one H is attached, that is a formic acid. If CH3 is attached, acetic acid, propionic acid, butanoic acid, propanoic acid, all are acid because COOH group is attached everywhere. Then this is making one family, that is the homologous series. Then now I think you have understood about the homologous series. Now I am talking more about the homologous series. A group or a series of organic compounds, each containing a characteristics function group, forms a homologous series, and the members of the series are called homologue. HOMOLOGUES. Homologous series is there. GOUS, that is homologous. This is the here LOGUES, homologous, that is the member is called homologue. Then different groups are there, then different homologous series are there, and each member is called homologue. Okay, the members of homologous series can be represented by a general molecular formula, and the successive members differ from each other by the molecular formula. They will differ by each other in a molecular formula by a CH2 unit. All will differ by one CH2 unit will be either less or more. All will not have the same number of CH2. Maybe one may be more than first, and other again more than second, more than third. CH2 will increase every time. One example I am telling you, CnH2n plus 2. This is the alkane formula, CnH2n plus 2. If we will, n is the number of carbon, suppose n is equal to 1, then Cn H2n plus 2 means CH2n means 2n, 2 into 1 plus 2 means 4, CH4. Now if n is equal to 2, then it will be C2H6. Then what is the difference between this CH4 and CH4? 1 carbon 4 hydrogen. Now 2 carbon 6 hydrogen. Then what is the difference? In carbon 1 difference is there, and hydrogen, there it was 4, now it is 6. 2 difference is there. That means they are differing by CH2. Like that way, if C3H8 is there, if n is equal to 3, then in formula you put CnH2n plus 2. The Cn, n is equal to 3. Then C3 and H2n, then 2 into 3 plus 2, 8. C3H8. Then now C2H6 and C3H8. What is the difference? Then that was C2, here is a C3, then 1 C difference, and there was 6, here is a 8, 2 difference, 2 H difference, then CS2. Then this is the example of homologous series. They will differ only by CS2. Whatever may be the group, functional group may be different, but difference will be of this only CS2. Then this I have told you about the homologous series. There are a number of homologous series of organic compounds. Some of these are alkanes, alkenes, alkynes, haloalkanes, alkanoids, alkanals, alkanones, alkanoic acid. These are the different series. Okay, these are the different homologous series. Just I have given example. Alkane example formula I told you, CnH2n plus 2. Like that way, one more formula is there for alkene, CnH2n. Like that way, third for alkyne, CnH2n minus 2. Then like that way, for each homologous series, one formula will be there, and with that formula, that some special group will be attached, functional group, maybe OH group, maybe other group, aldehyde, carboxylic. Then actually there is a standard group name, group we are calling according to the IUPAC name. Okay, standard name. Everywhere, all over the world, people will know by the same name. Okay, then that's why I told you these are the standard homologous series. Alkane, everywhere, all over the world will know alkane. Alkanes means what? It is fixed. Alkanes, ANE, alkanes. Alkane, alkenes, alkynes, haloalkanes means halogen group will be attached. Alkanoids, alkanols, all, alkanol, all means alcohol, shortcut. Alkan, with alkane group, alcohol will be attached. Then alkanol, many alkanols are there, then you can tell alkanols, S you can add. Like that way, AL means aldehyde, shortcut. Aldehyde is known as AL. Alcohol, shortcut OL means alcohol, AL means aldehyde. Hence you can with the alkane, ALKANE, then in the place of last two you can remove an other group. You can last two you can say letter you can add. 2 letter you remove and 2 letter you add with other groups. Okay, then that it is a scientific way to write the different homologous series. Then I told you alkane, alkene, alkyne. Now haloalkanes. Like that way, in alkane, when OL is added, then it will called alkanol. Alkanol. And if aldehyde group is attached with alkane, then alkanal, Al and the end, alkanal. And if a ketonic group is attached, CO group is attached, one, then that is called one. Then alkane, ONE, alkane, you can write alkane one. Then now 3 letter you have removed, ONE has come, alkane, E you have removed, alkane, E you have removed, ONE you have add, alkane one. Now alkanoic, OIC you have added with the alkane, E letter you have removed, OIC you have added, alkanoic acid, that is a carboxylic group, COOH, in shortcut oic group. Then this I have told you. One more example like amine group. Then this I have told about the homologous series. Okay, today I am stopping only here, and next class I will start nomenclature of the organic compound. This is a very important concept. Nomenclature is very important, and many questions are asked in all examination. And so we will go in details, and it will take time also. In one class, nomenclature will not finish in one class. It may take 2-3 class only in nomenclature. This organic chapter is very big chapter. Okay, it will take time, more time. It will take time to finish this organic chemistry. Only nomenclature will take, I think, 2-3 class, 3 class minimum it will take. Okay, now we are stopping only here. Again we will meet next class. Thank you.